Well, I hope you all had a refreshing lunch break and that you're ready for the next round of exciting presentations. This talk is titled AI Archaeology, Reading Ancient Texts with Cutting-Edge Technology. For those people joining online, you will have the chance to ask questions. Just leave your questions in the Zoom chat. And for people here in the audience, we'll do a Q&A afterwards. All right, I think this Big Tech Day has a very special touch to it because today we're having two presentations here that delve into ancient secrets that have puzzled archaeologists for centuries and that are now being unraveled through the use of modern-day technology. In the morning slot, we had a talk about how non-destructive testing techniques can be used in order to detect hidden chambers in the Egyptian pyramids. And in this talk now, we will learn about how AI can be employed in order to read texts that is written in some ancient papyrus scrolls that were charred during the catastrophic volcanic eruption of Mount Vesuvius in the year 79. So for the first time in 2 millennia, actually, these texts were deciphered in the context of the Vesuvius challenge last year in 2023. And so this challenge is actually like a groundbreaking machine learning and computer vision competition. And our three speakers here, they stand here today in order to represent a wider community effort, which they have spearheaded by innovating AI technology that has won them several prizes along the way. Okay, so let me present to you our speakers. First, we have Casey here. Casey, you are, I'm very impressed, true polymath. A physicist, an inventor, and an entrepreneur. You're actually running a company called Terraform Industries, which is where you're trying to scale up the production of a device of your own invention, which is called the Terraformer. And it has a goal to, well, it actually does already, it's working. It synthesizes natural gas just from sunlight and air. And it's a very ambitious goal. And I guess you are very busy, and if you are busy like that, you need a good free time activity to get some balance in your life, so you participate in coding competitions. And in the Vesuvius challenge, you were actually the first one to detect ink in the X-ray scans. All right. So next we have Julian from Switzerland, Julian Schilliger. You are, you just recently graduated in computer science and robotics at ETH Zurich. And you have recently decided to turn that newfound fame from the Vesuvius Challenge into a full-time career as a digital archaeologist. And finally, we have Yusuf Nader, a PhD student in computer science at the Freie University. And Yusuf, you have been among the first people to decipher actually an entire paragraph in those scrolls. And together with Julian, you were part of the winning team, of the overall winning team in this competition. And now I somewhere in here have a quote, which I wanted to read to you because this is how the host of the Vesuvius Challenge commented on your success. And I found it very inspiring, so to set the scene. The thoughts of our ancestors, locked in mud and ash, hidden in darkness, now with the light of a worldwide effort shining up on them, finally seen again. This is going to be really cool. So everybody, please welcome with me Yusuf, Julian, and Casey.
Thank you, Sven, and thank you all for really providing the opportunity for this honor to speak to such an incredible group of people working at the forefront of technology. It is truly almost a dream to be here and get to share with you some of the exciting stuff that mostly the other guys worked on. Anyway, so what you can see here is an actual photograph that was taken of Julian and Yusuf's work in an ancient library deciphering this artifact with a little bit of artistic license. So just to be clear here, there's some subtext, which is that you too can wear a cool leather jacket and a big hat and do archaeology, but you don't have to get dirty and dusty and hot and learn how to use a whip and stuff like that. You can actually do it with computers. This is super exciting because in a past life I studied classics for a number of years, but It's kind of hard work. There's no shortcuts to learning Latin, but it turns out that if you're already very good at computers, and all of you are, you can help make progress on this challenge. So a few words of biographical introduction. My name is Casey Handmer. I am from Australia originally. I have some photographs here of me doing various things like climbing volcanoes and visiting sculptures in Siberia and jumping out of planes and things. A lot of rocks. It turns out that rocks and old stuff is kind of a recurring theme. I had a career in academia once before I burned it up, but I mostly worked in gravitational waves. And I once managed to get this image here of me having a lightsaber fight with my advisor into a reputable journal. So that was pretty fun. And that's actually a rendering in the background of what two colliding black holes might look like moments before they collide. This was before Disney bought Star Wars, so please don't sue me. I left academia in 2015 and was very fortunate to be hired by this guy here, Jim Coutre, who's actually now building a new airship company inspired by the incredible work Germany did in the 1910s and 20s with the Zeppelins, into Hyperloop, which at the time was trying to revolutionize transport by building high-speed vacuum trains. And I got to work on a whole variety of super interesting stuff there, including some routing analysis and helped to figure out the shape of this tube. You may be getting a picture here that I'm a giant nerd, and that's true. After that, I got to work at NASA's Jet Propulsion Laboratory. So NASA is actually about 15 different centers across the United States, and the one in Los Angeles, which is in the lower left-hand corner of the United States, specializes in deep space robotics. And so this is me on my first day up in the mountains, just starting off, and I got to watch the Mars rover here being built. They wouldn't let me anywhere near it, of course, but it was pretty fun. And then here's the back shell right next door being built. The sky crane. And then here's a photograph of an actual alien spacecraft landing on a planet, where, of course, we're the aliens, which is pretty cool. And at the time, my wife, Christine Moran, who's much more talented than I am, was actually working on this mission. And so we got to, even though it was COVID lockdown, in a home office, we got to see those photos come down immediately, which is pretty cool. But 10,000 generations of humans have lived and died, and only one generation, our generation, has ever actually operated nuclear-powered robots on other planets. But anyway, after 4 years, that was me. Time to go. As Sven mentioned, I founded a startup in Los Angeles. Yes, it's actually in a castle doing synthetic natural gas from sunlight and air, but that's not the topic of today's talk. So here are a whole bunch of super cool people involved in the Scroll Challenge. Not everyone who worked on it, including Yusuf, unfortunately, was able to make it to this event. But the really cool thing, and the point of this photograph, apart from that's me and Julian's there, is that this building is actually a life-size replica of the Villa of Papyrus in Herculaneum that was built almost exactly 2,000 years after the original by Getty, John Paul Getty, the oil, he was pretty old by that point, but anyway, the oil guy, because he likes old stuff. And so we got to hold this event at the Getty Villa, which is pretty cool. You can't actually visit the original one, it's still mostly unexcavated. Oh, and then the third winner of the prize is Luke Farador here. So don't confuse me with the people who won lots of money. I'm still poor. So the way this started out was this guy here, Brent Seals, got interested in using advanced technology to read ancient scrolls. And the one we see here is one of the Dead Sea Scrolls that was considered too damaged to be unrolled. And so with his collaborators, he was able to scan it in essentially advanced CT scanner, very similar to one that you would use in a medical application. And then we got lucky because the ancient scribes in Judea used an ink that contained metal ions, in this case probably iron. So a little bit of rust was in there, which of course lights up like a Christmas tree under X-rays, as everyone knows. And so we're able to read the text. If you can read Hebrew, of course, you can read the text there, which is pretty cool. And then, of course, he, like everyone, knows about the ancient scrolls in Herculaneum, so he's like, I bet that would work really well. But it didn't work super well. basically the ink that was used in this library did not have metal ions in it, and it was very hard to see. But Nat Friedman, who is the current chairman of GitHub, which you will probably have heard of, got interested in this project. He's also an investor in my company, which is how I became aware of this project. And he decided to try and solve it using a prize. And this is why you should see yourselves as someone who might be able to work on this, because if you succeed, you too can make a lot of money. And so he put together this prize and then basically dynamically updated and structured this prize as time went on to try and incentivize smart people from all around the world to come in and try and solve the problem. So what is the problem? We all understand that there are few higher callings in life than thinking about the Roman Empire. But it turns out that rich people before the birth of Christ and rich people today share a couple of things in common. And one of them is that they like to brag and show off their good taste and convey prestige upon themselves by building beautiful things. And one of those things, or some of those things include artwork and sculpture, like we see on the right. This is actually this is actually a bronze from the Villa of Papyrus that's more than 2,000 years old. So you build a beautiful library, and these are, I can't work buttons, okay? It's not one of my skills. These are some more contemporary libraries here in Europe. But the same basic idea applies, which is you can fit a lot more fancy stuff in a given area of library than you can in a given area of art gallery. So you kind of combine the two functions. Anyway, it turns out that 2,000 years ago, there was a man called Calpurnius Piso, who was the father-in-law of Julius Caesar. And he was quite rich and powerful, and was also a known patron of the arts. And so he had this villa built in roughly 80 BC, down on the shores of the Bay of Naples. And this is a reconstruction from the excavations that have been done. And here's a similar one. We're not quite sure where the shoreline was prior to the eruption, but it looked something like this. Not that different to a modern luxury villa in many ways, but it contained within it a library that was not just a library that stored books, but it also stored writers. Because if you're really, really rich, you don't just have nice stuff, you also have people making nice stuff in real time for you and following you around. And we know about this because another contemporary poet and writer, Catullus, actually wrote about this guy and some of his friends who were in his employ kind of as patrons, which is kind of cool. All right, so we all know what happens next. Here's some photos of me in a previous life climbing Mount Vesuvius. The modern crater is left over from the eruption that occurred in 1944, and this is a painting of an eruption that occurred in the 1800s. But the same basic idea. It's a very active volcano. It erupted in 79 AD, and everyone involved had a very bad time. And one of the consequences of this eruption was that a bunch of ash and stuff flew out of the volcano, went down on this side and buried Pompeii, and then a bunch of really hot mud came down the hill here and buried Herculaneum. And this little square here is the ancient, well, the excavated part of the ancient city of Herculaneum, and then this is the modern town of Ercolano, which is just waiting for the next eruption. And the Villa of Papyri is just here. So it's very much adjacent to the old town, which it obviously depended on. In those days, there was no DoorDash, so if you needed food, you needed to be close to a town for services. So yeah, anyway, all this mud came down out of the volcano, and it buried the town to a depth of about 6 meters and extended the coastline out a fair way. And actually, Pliny the Elder, who was an early Christian historian, died on the beach here somewhere, according to his son. All right, so this is what happens when your ancient library gets toasted by a volcano. So what's happening here is mud is basically flooding the house. The mud is around about 600 degrees Celsius. So it has two kind of consequences to your library, which is made of scrolls. The first is that it seals it off pretty well, which prevents it from burning, which is important. And then it makes it so hot that the water molecules come out of the papyrus structure. I had some here somewhere. That's on the T. Okay. Now here's some authentic ancient papyrus that I bought on Amazon. But this is what it looks like. It's made from a plant in Egypt. That's where we get the word paper. Anyway, so it gets sealed up and carbonized and destroyed, and at the same time preserved, which is one of the reasons why this is the only known ancient library that has survived. Here's a map of the villa and the excavated parts. This was excavated in the 1700s. Not completely. About half of it is unexcavated, so there's work to be done. Oh, and by the way, almost all the scrolls that we have, about 600 in total, were discovered in, like, I think, this little closet here. We're not quite sure why they were all there. This is what the town of Herculaneum looks like today, with the volcano in the background. And this is what one of the scrolls looks like. So people were looking at these initially in the 1700s, and they thought, what is this? Is it some wood? We'll just burn it. And then someone realized, oh no, that's papyrus. It has letters on it. This is an ancient library. And then they got pretty serious about preserving it. But it's also, you can tell it's had a hard day. This is one being weighed. As you can tell, like, they're kind of banana shaped, and that might be from the eruption, but also it's highly likely that the ancient scrolls were not all in very good condition in the first place. And this is the result of, let's say, old-fashioned attempts to unroll them. And actually, some of these have been unrolled and read, and you can go and buy books of the text that have been recovered from them, mostly in ancient Greek. But it's obviously highly destructive, and we'd prefer not to do that. And so the crazy thing is, about 600 scrolls remain unopened, preserved for posterity, because even 200 years ago, people knew that maybe in the future we would, become almost godlike in our technological power and be able to recover the data. And so what we did most recently is scan it, make a digital copy of it, which you can download off the internet, and then basically tear it apart inside your computer without worrying about destroying the actual ancient artifact. And so the way this is done is Nat Friedman chartered a private jet to fly 4 scrolls from the conservation site in Naples to the UK, where they have this alien spacecraft, which is actually a synchrotron, which produces extremely energetic X-rays to conduct the scans. And this is what one of the scans looked like in my computer about a year ago when I started working on this. The file name is Vesuvius unwrap 6, because that's how I do version control. Look, I'm a man in a hurry, all right? So one of the major problems, which Julian will talk about, is unwrapping the scrolls. It's obviously highly non-trivial, and these red lines are the remnants of an attempt that I made to do this fairly ill-advisedly. But what I eventually realized was that thanks to the hard work of Julian and a bunch of other people, some of the partially unwrapped scrolls, I basically couldn't write code to detect the ink any better than any of the other people could, but maybe I could just stare at it for a very long time, which is what I did. It turns out there's like roughly 7 fundamental textures that are present in the scroll, and I was able to train my vision to distinguish between them and eventually detect ink in a very, to me, compelling way. But I think Nat and the others thought I was crazy for quite a while. Probably still do. And actually, I believe that Yusuf's model was doing the same thing, but with technology instead of with brute force, which is cool. And then here's a little video that I made that shows my process, and then kind of patches it into the work that was done by Luke and Yusuf later on. So this will tell you I'll show you how the process of discovery worked, and I'll provide a voiceover. So this is what the CT scan looks like. And you just kind of pan around looking at stuff, and then scrub through the layers. And there's kind of crackled texture there. It looks like a dried lake bed. So I got out a Sharpie and started coloring my computer screen, because again, in a hurry. And that looks a lot like a pie to me. And then I did this with the adjacent letters and realized that this is almost certainly text, right? It's rows and rows of text, and then this is it overlaid with the computer-detected ink. So obviously my approach does not scale very well, but once we can train a computer to do this, then it is possible to read, in this case, thousands and thousands of characters, hundreds and hundreds of words of ancient Greek text, in a scalable way. And just to put this in context, right now, if you extrapolate the current methods, it will cost about $1 million to read one of these scrolls. Now, if we just had a few scrolls, well, that's pretty good going. There's not that much ancient text. But there are actually hundreds of scrolls, and I would very much like to have translated, annotated versions of them available before I die of old age. So it would be good if we could find ways to further automate this. No pressure. So these are the winners of the grand prize, and this is the complete the complete text that was discovered as of earlier this year on scroll 1, that represents about 5% of that scroll. So getting towards the end here, of my section at least, Elon is of course aware of these problems. Only 1% of ancient literature has survived. This is the Lerb library, which is a curated, translated version of essentially all of the ancient text that we have. The green is Greek and the red is Latin, and each of these books contains a fairly lengthy introduction, a hardcover, and an English translation on alternate pages. So the actual amount of ancient text that has survived from the ancient world through the medieval monks copying stuff is, if you boiled it down, would probably fit on 3 or 4 shelves. That's it. That's everything that we have. That's all the Cicero, all the Pliny, all the Caesar, inexplicable quantities of very strange stuff. And essentially anything that the medieval monks didn't like or didn't think was appropriate. So we're talking almost all the writing by women, almost all the writing on ancient science, for example, almost all the writing about non-Christian rituals, for example, did not survive, except possibly in this library. And here's a model that I put together illustrating what might be waiting. So the blue bars represent what we have, and the red bars represent what would be in the library if they bought everything that was available, a representative sample of everything that was available when the library was built in 80 BC, and then curated that for 160 years before its destruction. And that's only 25,000 scrolls total, which is equivalent to roughly 2,500 books. So Thomas Jefferson's private library, which was curated in about 1800, was about that size. And given that Calpurnius Piso was far, far richer than Thomas Jefferson was, it is plausible that his library was much larger too. We know of at least 2 other libraries in this area that were also destroyed in the eruption. We don't know exactly where they were, but they're out there somewhere. We have 600 scrolls from this library. There could be thousands more still underground. Right now we've scanned 4 of them, and we've read 5% of one of them. So there's a lot of work to be done here. Yeah. I'll just kind of point out, this is what the raw data looks like if you're trying to identify some of the crackle features over here. You'll see them kind of coming through. So, this doesn't require, I don't know, like, maybe it just makes me look like a crazy person, but like that's almost certainly some ink there and then over there. So this is from one of the other scrolls, which hasn't been read yet and largely hasn't been unrolled yet. All right, let's skip to the end. I think this is my last slide. So the current prize pool is over $2 million, and it is sponsored by Elon Musk, who is very generously putting up some money, but he can afford it. And regardless of what you think of him, we can probably agree that if we were to win those prizes and make him $2 million poorer, he would be okay and we would be okay. So, and obviously posterity would like it too. So with that, I'm going to hand over to Julian for the next section.
Thank you. Hello, everyone. It's really nice to be here. My name is Julian Schilliger, and a little bit something about myself. I really like being in the nature, being in the River Rhine, and always I have a little side project from time to time, like, for example, a robot that I program. Or last year, my side project was the Vesuvius Challenge, which I then won with Youssef Nader and Luke Fariter. Youssef is actually the team lead and also here. So why did I join the Vesuvius Challenge? At the time, it was March 2023. I was doing my master's thesis at ETH Zurich. I was programming as a rather cool robot that goes to the greenhouse and picks tomatoes. So I was in the greenhouse, I was on my computer, I always saw tomatoes. I tried to classify how ripe is one tomato, how ripe is a bunch of tomatoes. I had a lot of tomatoes on my mind and I needed a change of scene, so what better way to have than to have a private research project that I could work on. And I joined the Vesuvius Challenge. Lots of nice people there, and there were 2 remaining technical problems that still needed to be solved. The CT scans were available, you just had to download them. Well, you had to also have the time and the storage capacity, since one is like 1 terabyte to 4 terabytes of data. But still, there are two problems, unrolling them and then reading them actually because the ink doesn't show up. And I decided to go for unrolling. So the state of the art at that time was 200 years old, and it was called Piaggio's machine. It was using lots of iteration also by destroying scrolls actually. Unrolling them physically is really destructive. Here you can see on the top right here, that's a good unrolling, right? You can read a lot of text, that's an infrared image, but then on the bottom here, lots of text is lost forever, and yeah, generally it looks like that. So the CT scan, if you just slice through the data, it looks like this, a little bit like a tree stump, but actually it's not a tree ring, it's more like a spiral. So here I show one spiral, how it looks like, and that's the surface that we want to track. So that is the problem of segmentation, a little bit of a different definition than usually what segmentation means, but here it means tracing the papyrus in 3 dimensions. Here it is done for 1 dimension. If you then virtually unwrap this scroll and flatten it, it looks like this. And going closer in, you can see really the papyrus fiber. So the papyrus plant, their stem was sliced very thinly, and then one set of roots or slices was laid horizontally, and the other one vertically, creating this grid pattern that you can see, but no ink so far. So there is also some previous tools that was used by the University of Kentucky researcher to extract some surfaces, and I was eager to try them. The tool was called volume cartographer, and the idea behind this is to manually track the surface with a curve and then have the computer iteratively propagate it through the volume into 3D. Whenever the computer loses the curve from the surface, then you would go as a human, label again, and adjust this curve to the surface again. It's really labor intensive, but it was the way it's done. And it was called Volume Cartographer, the tool. But the initial version, it was really, really clunky. It was slow, and it crashed often. So it was really not nice to use. And since it was really, really slow, it also wasn't able to create usable segments. So the maximum segment that you could do, maybe if you just like spend a week of it, just segmenting it, then you had like 1 letter, so not really scalable. That's when I started, and I thought about let's just iteratively refine and improve this tool. Update the GUI, make it less often crash, have a better interface to adjust the curve, just basic improvements to the productivity. That was one side. And then the other side was better algorithms. For that, I used optical flow. I said like, okay, you have this 3D image, but maybe you can just have the 3rd dimension instead of a spatial dimension, you would have a time dimension and look at it as a video, right? And so videos, you have prior art there for optical flow. You can have the movement of pixels, like the movement of sheets, and therefore adjust the curve better. And by iteratively testing and updating my algorithms and have people give feedback to that, I added some magic little sauce that made it better and better over time. And I guess if you look at the reasons why this was the way to go, here you can see the papyrus surface, how much it was segmented at any time. First of all, it was an interesting problem, so I kept at it. I kept improving, iterating, and just like had fun. It was a hobby project. And then I had users that really had their hair burning. They wanted to have improvements. They were willing to test anything. So I gave them something. They gave me feedback. And I developed it in the open, which meant that everyone could improve it or update it. Also, the code for Volume Cartographer was open source. And that was a good thing, so I could just go in there and change whatever I didn't like. I get feedback, and the fast iteration cycles meant productivity was going up steeply. So performance was measured with the area segmented. That was really easy and a good way to keep track of. You can kind of see that the performance is kind of linear. That is because the segmentation team, there were like 3 to 10 people actively working for actual money that were employed at the Vesuvius Challenge, doing their stuff. They pushed the surfaces and they went for the easier ones first and then the harder ones, and I developed at the same time. So in the end, I had a 10,000-fold improvement to the first version. But yeah, segmentation, that's not really scalable if you want to read a lot of scrolls. So tracing costs a lot, a scroll costs a lot to just unroll, and if you have 800 scrolls, that costs like 3 Colosseums worth of money. I went back to the drawing board and started fresh. I had lots of ideas and I learned a lot of things at developing. So I really focused on generalization, abstraction, and automation to get the costs down as much as possible and have a tool that automates these things. I defined smaller subproblems, exactly first off just extracting where the surface actually lies more exactly. Then I have a point cloud that doesn't have any connectivity, so I connect those point clouds to surfaces again, and then mesh and flatten them. The intuition behind the surface, if you look at the CT scan, the air is black, and because of the higher density, the papyrus is white. Then the intensity curve is like a bell curve, where the inflection points actually correspond to the surfaces. Yeah, so those are some point clouds, how they look like. It looks a little bit artsy. The one on the right is really just a slice through the scroll, and I just showed you in red some surfaces, how they would follow those data sets. So the data is this big. I used cubes. I blocked it to have processing in smaller cubes to have it more accessible and haven't had to load everything into the computer RAM at once. And if you look at it here, that's how it would look like, the data. So you, as a human, you can see in this block where the sheet approximately is. But as a computer, it's really hard. Those are just points. Luckily, in my master thesis, I used lots of tomatoes. Maybe that's also why the tool is called Tomato Uncollector. That means Miracle Uncoverer. I also had 3D instance segmentation that I used and that I could use here again. So I created training data and trained my model for those small patches. After that, well, I have some small patches now for the point cloud connectivity, but how do I do this in a global step? So I need to stitch those patches together into large sheets. And this is a problem called minimum feedback arc set problem, and in general, sadly, it's NP hard. But for some cases, for example, if you have a graph that is planar, it's actually just, it's not NP hard anymore. For our case, I don't know, but I'm using randomized algorithms at the moment. I'm not sure what's the best solution, but those work. I don't need a perfect solution. I just need to be like 95% there, and the rest is okay. And then in the end, if you have this connectivity, this is how the scroll looks like. And zooming out, you can see how it looks if you unroll it, if you flatten it. That's the current state, or the state where it was at this, like in January. And a small part of it, when you unroll it and texture it and do ink detection on it, here you could see some letters, but it's not perfect. Like the manual segmentation is still much more accurate, and this needs to be improved. So in the spirit of this challenge, I implore you all, if you have time and you have like an interest in this, come work at it. Join us. Go check out scrollprice.org. And with that, I give over to Youssef.
Hello, everyone. So my name is Youssef Nader. I studied communications and computer engineering in Cairo University. And during the final years of my bachelor's, I realized that I really like machine learning through AI competitions. So I decided to do my master's in data science at the Free University in Berlin. And I'm currently a PhD student at the same university. And I generally work on machine learning, explainability and explainable AI, and self-supervised learning, which doesn't really have anything with what we're talking today. So how did I get involved? One day I was regularly checking competitions on Kaggle to see if something interesting came out. And I came across this challenge. The Vesuvius ink detection, resurrect an ancient library from the ashes, and win $1 million. So I was like, OK, where do I sign up? And I started following the Vesuvius challenge. And while the Vesuvius challenge sounds like this monolith challenge, it was actually broken down to multiple sub-problems. And we saw that there was the track of unrolling the scrolls, which Julian worked on. There was also the track of ink detection. And this track started with the Kaggle ink detection competition. The Kaggle ink detection competition looked at small fragments of the scrolls that broke off. So these are fragments that we can see actually the ink if we look at them. And we can use infrared imaging to have a clear image of the ink. And we can also apply the same pipeline that we use for the scrolls with X-ray CT scans and unrolling to also have the 3D volume or the 3D image. And we can try to train machine learning models to detect this ink, and hopefully, since the scrolls also undergo the same process, they would be able to see the ink inside of the scrolls. So this is how the machine learning model operates on a certain fragment. It operates in these small windows, these small cubes, and tries to find, does this place have an ink or not? Does this place have an ink or not? And when you move the window all over the fragment, which is thousands of pixels by thousands of pixels, you get a clear image of what the ink looks like. So the Kaggle ink detection was sort of benchmarking our progress. How well can we make machine learning models to find this ink? And you will see that the first image is from the ink ID baseline, which is where the state-of-the-art was before the competition. And after the Kaggle challenge, the top 10 winners, their submissions were averaged. And you can see how the signal-to-noise ratio has improved. The letters look clearer now. And especially those last two lines look much better. But we were still a bit far from having the full ground truth. And the bigger problem was actually not in the performance, but for the scrolls, the unopened scrolls, these models were still unable to see anything. And I was just finishing up my master thesis when the Kaggle competition concluded. So another competition for the ink detection started, which is the ink detection follow-up. And this is my solution for this problem. We know that going from these Kaggle fragments to the scroll does not really work. But what if we can somehow learn something from the scrolls before we start applying these fragments and learning from these fragments, so that the model is able to perhaps adapt and say, yeah, I've seen this part before, and if it's seen it before and it's ink, then it's maybe able to make this relationship. This idea, while promising, it didn't really work, but it didn't really not work either. So the idea was to apply self-supervised learning on the scrolls, the same way our brain can realize that this is the same image if it's rotated or flipped. If you see your dog like upside down, you know it's your dog. The same way for ink, it's still writing if you rotate the image, right? And the model should learn that there are some properties in this image that don't really change when some transformations are applied. The representation, the numerical representation that the model learns from an image and its transformed partner, it should be the same. And this approach was able to push the limits of these models to just finding barely the first couple letters. So I spent a lot of time on trying to improve this approach, but in the end, there was something holding it back called the uniform cluster prior, which is just a fancy way of saying the model couldn't care less about the ink. So one way to make the model care was to, OK, I already do see some letters. I'll just tell the model that these letters is ink, and I'll just train it again on these letters. So I took this model that could barely find a couple letters, and I created a label map, which is just telling the model where the ink is in this image. And this image is not really accurate. You can see there's this epsilon, lambda, epsilon at the top, which is pretty much my own delusion. And it's not really ink, but it was OK to train the model on this. So the model takes this image. It's fed to a new model that is now trained that this is actually ink. And from this first iteration of taking this new information about what the ink in the scroll looks like, just these couple of letters, the model improved, and there was now so much more letters. So I thought to myself, well, what are the chances that if I do this again, the model keeps improving? And it turns out that there are ways to keep the model improving without actually having the model become the previous model. So one thing we don't want to happen here is we don't want model 2 to just learn what model 1 does and just be stuck in a loop. The models don't get better, they don't learn about the ink. So this is a problem commonly known as overfitting. We're pretty much giving the model some data that is wrong, like that epsilon, lambda, epsilon. And we want the model to actually learn what ink looks like in the CD scans. So I tested a couple different ideas to see how I can prevent the models from overfitting. And it turns out that smaller AI models that have less capacity of memorizing stuff work much, much better and are much harder to overfit, because when you make up a lot of things, it's very hard for them to keep up with these delusions. Another idea was how to make it easier for the model to make mistakes and disagree. And this was done through label smoothing, which means reducing the probabilities of these labels and balancing the data sets, creating many variations of the images. So the idea behind label smoothing is that mistakes can happen during labeling. I introduced some labels. I don't know any Greek. My Greek knowledge is absolutely unreliable. So when I'm creating these labels for the model to train, they will contain mistakes for sure. And the model should not be penalized when I'm the one making the mistake in giving it the data to train on. And the model should have some flexibility to disagree when I'm making a mistake. So the idea was to reduce the probabilities. This is not really ink with a very high probability. This is ink with some probability, and this is not ink with some probability. So if you have a letter O here, and please don't tell the papyrologist that I call this an O. If it's incomplete and I don't see the rest of the letter, the model will actually be trained that this red part is empty. But it might be able to see that it is not empty, and it should be able to make these predictions. Another idea was how to balance what data to give the model. If I just give the whole scroll to the model, this actually contains a lot of data that we haven't read yet. So this would introduce a lot of false negatives. The right balance turned out to be taking a small area around each letter, such that the model sees what not having letters look like, what the scroll and the papyrus looks like, but also has a nice balance of what the ink looks like. And this prevents the model from becoming lazy, like not everything is letters, but also not everything is not letters. Another important question was, how do we choose how much data do we show the model at each time? When we're moving this window all over the scroll, how much should we show the model? And we tested many different window sizes. And it turns out that giving the model a large window that it can see the full context of the letter was actually something really hated by the papyrologist, and something that allowed the model to do some interpretation. It now doesn't really rely on what the ink is, but it also memorizes my own handwriting, which is not really great. And to prevent this from happening, we mitigated this by choosing a very small window size, a 64 by 64, when the full letter is around 512 by 512 pixels. And you can see it takes the model quite a lot of time to build up the full letter. And if the model agrees in every single time that there is ink, you will be able to see the letter and interpret it as human. In the end, I was able to win the second place in the first letters prize, and I was able to uncover the first word from the unopened scroll, which was the word purple. The method was open sourced, and the grand prize race was on. So the big question was, how do I scale from the first letters to the grand prize? And there were two main points to get to a point where we actually have a lot of text coming from the scrolls. The first was how to get as much quality data as possible, how to improve this process that I'm doing with the labeling. And the second was how to train the models to make the most out of the available data. So to scale up the amount of data that we have, and as Julian mentioned, we had the segmentation team continuously working on producing these large chunks of the scrolls. I did more than 15 iterations of this pseudo-labeling round. Every single time I train a new model, the new model produces somewhat better signal from the inside of the scroll, and we take this signal and train another new model on probably more data. I explored a lot of labeling techniques and data quality effects, and the biggest conclusion was it's actually better to give the model these kind of hallucinations or delusions from me when I'm not really certain if this is a letter or not, but I'm pushing the model to investigate in this area, rather than give the model a large chunk of letters that it's able to predict very well. Because this is something the model already probably knows very well, but the areas where it's uncertain about the ink is what's most valuable information for training the model. The second idea was, how do we scale the models to make the most out of this idea? And our winning model in the end was what's called a timesformer. And the timesformer explores this idea of, if we have this kind of 3D data, what's the best way to model this data? Is it best to model it as a 3D full object or a sequence of 2D slices, or maybe some insane ideas of the nearby pixels and the far pixels? And the thing about timesformer is, which was a little bit counterintuitive, the best way was actually using less data. So transformers generally chop up images into a bunch of patches, these small rectangles, and try to learn what is the relationship between these patches and one another. And the paper basically found that using just your neighbors in the spatial dimension, like this slice, this volume slice, and by comparing yourself throughout the depth of the scroll, this would actually achieve the best scalability and performance. And in the end, this model was able to read more than 2,000 characters from inside of the scroll. And we now have some quotes from Philodemus ranting about probably Epicurean philosophers and saying that they have nothing to say about pleasure, either in general or in particular, when it's a question of definition. And if you go to scrollprize.org today, perhaps you can join the effort of retrieving more philosophy rants and maybe perhaps a more interesting text. Thank you.
Thank you very much, Julian, Yusuf, Casey. That was really fascinating, and to use the phrase of Julian, I had my hair burning. So we have time for questions now. I can see a question here.
Will it be possible to generate a modern role, like printing something on papyrus and then trying to replicate the process of putting the lava over it to get better training data?
Yeah, some people have been trying that. But we kind of beat them to the punch. So I should probably outline what has to happen here. Like, we have this process, all these steps need to be improved, right? But in terms of the really time, labor-intensive one right now, it's the unrolling, digital unrolling. Then there's the ink detection. You know, we have a pretty good idea how to do that. Then there's character recognition. There's filling gaps and holes in lacunae. There's translation. There's commentary. ChatGPT can help out with that one. And then obviously there's the scanning process itself at the very beginning. We may have to build another synchrotron down in Naples so we can scan 600 scrolls. But I just want to press one button and like the 1 terabyte file just turns into translated text. Like, that's what I want.
Our goal is to go from ash to text. That's also one of our website's links.
Yeah.
All right, I have another question. How do you know if you're right in the end and not maybe missing a page when unrolling, or maybe your page you unrolled is actually 2 pages together? And also, how do you know that the text the model is outputting is actually what's on the scrolls? It could be like a random Greek text model comes up, right? Is it just a chance, or that the chance that you randomly produce text that is like sensible Greek is so slow, so slim, that if you produce like any sensible Greek text, it's probably right? Or how do you verify it in the end?
So for alignment, I can talk to you about the first part of your question, about if you know whether you switch the sheet. Just looking at the columns, the column always starts with a specific interval. You have always the same distance between 2 columns. So if you go and count the distance between consecutive columns, you can kind of see, here, the start of the column is always the same distance. You kind of can see if you switch the page or not, if this isn't the case. And the second part I give over here.
Yeah, for knowing that the model is outputting the correct Greek, the model actually doesn't know anything about Greek either. It's operating on a very small scale that we know the model doesn't know at any point like what letter it is coming out. And then once the full prediction on the full letter is done, we can look as humans and as papyrologists, we can look, zoom out and see that what came out is Greek. But for the model, as much as it's concerned, it could be any language. It's just trained to detect the ink, not the language itself or the letters.
Yeah. One of the nice things about handwritten text is that there's a lot of entropy there. So if it was hallucinating, it would have to be hallucinating extremely well for us to be fooled by it. But that's why one of the reasons why, like in this section here, where a lot of the ink is pretty obscure, so like there's work to be done on ink detection, for example, we can still reconstruct that because there's only a couple of words per line here, and each word only has 1 or 2 bits of entropy. So you can fill in pretty large gaps if you have the context of the surrounding section.
All right, thank you. Are there any more questions? Oh, way back there. Maybe in the between time I can ask a question as well. Can you speak a little bit about the dynamics of the competition? Was it always easy going for you? Were there ups and downs? How did you collaborate?
I think it was a very nice combination of a cooperative and competitive challenge, which is not what you see most often with AI challenges. There's all the time contributions coming out from amazing people, and at the same time there's this big prize and this glory of reading the scrolls at the end that sort of pushes you forward, but you're also incentivized to contribute. I met Julian throughout the Discord channel on the challenge, and we've become friends since then. And yeah, maybe you can talk about the collaboration.
Yeah, so you just get a lot of cool input if you open source your work. You get a lot of new ideas from people on Discord, and it's just generally a really nice and high-spirited area to be. Yeah, I really liked it.
Once they award the prizes for a given milestone, all the work that went into that is publicized. So like all the stragglers get brought up to the same level, and it kind of resets. And that's nice because it keeps like a wider team in the game. And this is one of the tricks that Nat and Brent used to make sure that the competition worked well, in addition to like paying for manual segmenting and stuff like that. Yeah. But the other thing is like the actual number of people working productively on this competition has never been a particularly large number. A number of people dip in and give up or try a bunch of stuff that doesn't work. That's mostly me. And so it actually, like, don't overestimate, like 1 or 2 people jumping into this with new ideas could really, make as big advances compared to what we have now as we have made since a year and a half ago. We're still very much at the early stages of this technology, and it's a great opportunity to really dive in and make huge advances.
So, thank you very much for your talk and your work. I have a very stupid idea. So what I heard in the talk, that thing that it's holding back is in this machine learning approaches that you have very few labeled data, as this is very label intensive to produce. I mean, could you just take a fresh papyrus, write something on it, and you already know what's on it, then heat it under oxygen-free environment, and then kind of like produce new data manually?
Some people have been doing that. We don't know exactly what the formulation of the original ink was, and it seems likely even that the formulation varies from scroll to scroll, which is annoying, but we will solve it.
All right, then I think we're done. Thank you very much to the three of you, and I think you will still be around for questions, chatting, and so on. So it was really fascinating.
Thank you.